Hello friends, myself PIYUSH and TANDEL, working as Assistant Professor in Electrical Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. And my name of subject is Industrial Instrumentation, which comes in 4th year, 7th semester. Right now we are talking about chapter number 1, that is transducer, and this is the module number 2. So starting with flow of content. In this session, we are going to study the dynamic characteristics of an instrumentation system, then after transducer and principle of transducer and classification of transducer. So starting with dynamic characteristics of instrumentation system. So in previous video, we already studied about the static characteristics of the instrumentation system. In that video, we discussed that in static characteristics, the value which we are going to measure is going to stay steady with respect to time. So what's going to happen in dynamic characteristics? The dynamic characteristics of a measuring instrument refer to the case where the measured variable change rapidly. So the measured variable is going to change with time. So that's why this type of characteristics is called as a dynamic characteristics. Now, the sensor in control system cannot react to sudden change in measured variable immediately. Suppose let's take an example of temperature sensor. Suppose the temperature of the surrounding is going to change very rapidly. Then the sensor cannot change or sensor cannot react to it immediately. Right? A certain amount of time is required before the measuring instrument in a control system technology can indicate any output based on the input received by the measuring instrument. So the temperature change that is happening in the environment, we require some time for our sensor to sense the correct value and give us a stable correct value. So it required some time. The amount of time depends on resistance, capacitance, mass and date time of the measuring instrument. So the value is going to depend on these different factors. Step response, ramp response, frequency response of measuring instruments determine the dynamic characteristics of the measuring instrument in control system technology. Okay. And now the dynamic characteristics of any measuring system are: first one, that is speed of response and response time. Second, that is lag. Third, that is fidelity, and fourth, that is dynamic error. Out of the above four characteristics, the speed of response and the fidelity are desirable in the dynamic system, while the lag and dynamic error are not desirable. So over here we need to note one thing that is very important. So out of the above characteristics, speed of response, that is how fast our sensor is going to respond, and the fidelity, these two are desirable in the dynamic system, but lag and dynamic error, because the lag in reading and dynamic error, so error, that is not a desirable quantity, right? So starting with the speed of response and response time. So how we can define speed of response? Right now the speed of response is defined as rapidity with which an instrument or measurement system responds to change in measured quantity. Now what does it mean? It means like how fast you can respond to any sudden change. Suppose we take one simple example. Right now you are playing a football game. At that time some of your teammate pass the football to your side. So you have to respond and collect that ball, and then after kick that ball again. So you need to respond very quickly. Suppose you are playing as a goalkeeper. At that time, whenever the opponent player kick the ball, you need to respond as fast as possible to block that ball. Okay? So at that time, the speed of response need to be high. So in our instrumentation system, speed of response need to be high. Now, response time is the time required by instrument or system to settle to its final steady state position after the application of the input. So whenever what type of input we are applying to our instrumentation system, it required some time to stabilize that value. Suppose we are going to measure the speed of our bike. If we are increasing speed of bike very rapidly or very speedily, at that time what's going to happen? Our speed is not directly going to indicate the correct value. It required some time to indicate the correct value of the original speed. Or we can also understand this by the same case of football. The final steady state value, that is, as if you are as a goalkeeper, at that time you need to block that ball. So you required some amount of time from your position to blocking position of the ball. So that total time is called as a response time. For a step input function, the response time may be defined as the time taken by instrument to settle the specified percentage of the quantity being measured after the application of the input. So after the application of input, the instrument need to settle down some percentage of the specified input. This percentage may be 90 to 99 percentage depending upon the instrument. For portable instrument, it is the time taken by pointer to come to rest within 0.3 percentage of final scale length. And for switchboard, or we can say panel type of instruments, it is the time taken by pointer to come to rest within 1 percentage of its full scale. Okay, so this is called as a speed of response and response time. Now next is measuring lag. An instrument does not react to a change in input immediately. We already know that, right? In previous slide we studied the same thing. The delay in the response of an instrument to a change in measured quantity is known as measuring lag. So the delay, that whatever the delay we are facing in our measuring system, is known as a measuring lag. Thus, it is the retardation delay in the response of a measurement system to change in the measured quantity. This lag is usually quite small, but this small lag become highly important when high speed measurement are required. So sometimes you need to respond very quickly with respect to your input. So at that time we cannot consider any kind of lag in our system. So lag is not that much desirable effect. In the high speed measurement system, as in dynamic measurement, it become essential that the time lag be reduced to minimum. So that's why this type of effect or this type of phenomena is not very much desirable in our measurement system. Now measuring lag is of two different types, that is retardation type and time delay. So what is retardation type? In this type of measuring, lag the response being immediately after the change of measured quantity has been occurred. Okay, and time delay, in this type of measuring lag the response of time measurement system being after a dead zone after the application of the input. So after the dead zone of the application of the input, the time delay is going to be observed. Now next is fieldity. Now fieldity of a system is defined as the ability of system to reproduce the output in the same form as the input. So whenever we are going to give the same amount of input, our output need to be the same, or we can say reproduce the same amount of output. It is the degree to which a measurement system indicates change in measured quantity without any dynamic error. Supposing if a linearly varying quantity is applied to system and if the output is also a linearly varying quantity, the system is said to be has 100% fieldity, because it is going to change with our input. So our output is directly proportional to our input. So it have 100% of fieldity. Ideally, a system should have 100% fieldity and the output should appear in the same form as that of input. And there is no distortion produced in the signal by the system. So whenever we are going to change our input side, there are no disturbance that is going to be created by the system inside of our signal. So whenever we are changing our input signal, our output signal need to be changed. That's why we can call as a 100% fidelity. In the definition of fidelity, any time lag or phase difference between output and input is not included. Now next is dynamic error. Now as the name indicates, we already know what is error. Okay, error is the difference between the actual value and the measured value, right? Now what is dynamic error? The dynamic error is the difference between true value of the quantity changing with time and the true indicated by the instrument if no static error is assumed. Right now, if we can consider as our instrument have no static error, at that time whatever the input value, the input quantity with that is changing with time, and the value indicated by the instrument that is also changing with the time. So the difference between these two values is called as a dynamic error, and at that time our static error is assumed to be 0. Now however, the total dynamic error of the instrument is the combination of its fidelity and the time lag or phase difference between input and output of the system. So if the dynamic error is going to be increased, our fidelity of the system is going to be reduced. It is simple as that. Okay. Now next is overshoot. Now moving parts of instruments have a mass, thus process inertia, because moving part have some inertia. Okay. When an input is applied to instrument, the pointer does not immediately come to rest at its steady state, or we can say final deflected value or final deflected position, but goes beyond it, or in other words overshoot its steady state position. Now what does it mean overshoot? Overshoot means, suppose we have our motor that is going to run at a 1500 rpm, or we can say 15,000 rpm, but whenever we are starting our motor without any kind of load, it is going to overshoot, or the rpm is going to increase more than the 1500. It is going to nearby 1555 or 1600. Then after it is going to reduce again, and again it is going to increase, and then after some point of time it is going to stabilize its original steady state value, that is 1500. So this oscillation is called as a overshoot. The overshoot is evaluated as the maximum amount by which moving system move beyond the steady state position. In many instruments, especially galvanometers, it is desirable to have a little overshoot, but an excessive overshoot is undesirable, because we cannot predict our true value when overshoot is going over there. Now overshoot response graph. For better understanding, we can look over here in the graph section. A typical overshoot response graph can be shown as the response time started in terms of rise time, peak time or peak percentage overshoot, and settle time. So we have three total time, that is response time, that is started in terms of rise time, peak percentage time and overshoot time. So from the figure, how we can say that over here our value is going to start from 0. So it is called as a initially steady state scale at a 0 value. Then after its final value is 100, but it is going to overshoot, that is called a peak value. So peak value is over here. Then after it is going to start reducing, because it need to reach at a steady state position. So it is going to reduce, and again it is going to be more reduced. So the level of steady state value and the peak value is known as a overshoot. And after some duration of time, the overshoot is going to be reduced and the percentage of output is going to be stabilized. Now, standard signals. The measurement system may be subjected to any type of input. Since in majority of applications the signal are random in nature, and the type of input signal cannot be known ahead of time, it becomes difficult to express the actual input signal mathematically by simple equation. To study the dynamic behavior of the measurement of the instrument, certain standard signals are employed for which the mathematical equations have been developed. These standard signals are, some of the standard signals are, first one that is step input, second one that is ramp input, third one that is parabolic input, and fourth one that is impulse input. Now let's study this all in detail. First, that is step response. When the measured variable of a measuring instrument in control system technology encounter change from one steady state value to the second steady state value, it is a step signal, and response shown by the output of measuring instrument is called as a step response. For example, when you change the temperature of the probe of a measuring instrument by shifting it from ice water to boiling water. So right now we are changing temperature from ice water to boiling water. A sudden temperature change could be observed in the output of the measuring instrument. The step response. So right now if we have our ice water, at the time temperature is very low, and at the other point we are moving it to the boiling point or boiling water. At that time the temperature is very high. So we are going from very low value to very high value. So it is going to, like, if we have over here our ice water and over here our boiling water temperature, so it is going to be sudden change like this, so increasing very rapidly. So this type of change is called as a step response. The step response of such a measuring instrument is started in terms of response time and rise time for over damped or critical damped situation. Now let's see it with the figure. Whereas for under damped situation, the term used for the measuring instrument are rise time, peak time or peak percentage, overshoot and settling time. Typical step response curve for an over damped or critical damped measuring instrument is shown in figure. So as we can see over here, it is going from 0 to its 100 value in very short duration of time. So this time t is constant and this is 95 of its response time, and over here as you can see 10 to 90% of rise time. So this time period to increase the value from 0 to 100% is very low. That's why this type of signal is called as a step input. Now ramp response. In ramp signal, the value of signal change slowly with time, not as much like in step response. So the typical ramp response curve of temperature measuring instruments shown in the figure below. The measured temperature lagged behind the input temperature, then caught up the input after a certain period of time. This figure allows us to view two response curve, the dynamic error and the dynamic lag. So as we can see over here, the temperature is going from the 0 value to its maximum value. But over here in first figure, this is the input temperature, that is the actual temperature that is going to be sensed by our sensor, and the another that is the output temperature. So this is the output, and the difference between this input and output is called as a dynamic lag at temperature T1. So this is at a temperature T1, and over here this is the output temperature, or we can say dynamic lag at temperature T2. So over here dynamic error at temperature T2. So this is the ramp response of temperature. Now dynamic lag of measuring instrument is the amount of time that passes between the time the input reaches a certain temperature and the output that follows input reaches also at the same temperature. A horizontal line T1, as we already know, T1, that is the dynamic response of the graph, interact with the input curve, and the small t1, that is the small t1, that is the output curve. The difference between these two times is defined as dynamic lag of temperature T1. So this difference is known as dynamic lag of temperature T1. Same as well as this difference is called as a dynamic error at a time T2. Okay. Now moving forward, these are some GTU questions that are important with respect to your examination. So I hope you refer to this complete video and find out the question from this video. If you have any kind of question, then please feel free to ask in comment section. Thank you.